presenting monitoring mechanical load in a military population using a single IMU. Thank you, Andrew.
Automatically detecting activity. Distinguished guests, ladies and gentlemen, colleagues, I'm very grateful for the opportunity to be involved in DHSS 2020. I'm presenting to you about an ongoing machine learning project which is aimed at automatically detecting activity type and bringing objectivity to the measurement of physical load. The project will address the need for a mechanical load sensing system in a military population that emulates equivalent practices presently being employed in professional team sports. I will cover an outline of the methods applied to address this issue thus far before briefly presenting the current results of the project. I'll then provide an explanation of the practical implications and conclude with a summary of the next steps, as well as providing some time for questions regarding the project. Before I start, let me clarify that this presentation will not include a detailed discussion of the data science techniques used. It will focus on providing an overview of the project purpose and relevance. Having worked directly with professional athletes for over 25 years and consulted across multiple team sports internationally, I've seen many changes during this time. In professional sport, athlete monitoring is now standard practice for managing physical performance, mitigating injury risk, as well as optimizing both competition readiness and career longevity. Monitoring load also provides a supporting scientific explanation for changes in performance and allows retrospective analysis of the load-performance relationship to enable appropriate planning for future programs. Monitoring systems attempt to quantify either the cause or the effect of load. Evaluating the stress of an individual from training and competition, the cause, as well as the effect that this load has on each individual. Researchers investigated many external load quantification tools to measure the cause, including time motion analysis, such as GPS tracking devices, force plates, power output measuring devices, linear position transducers, and more recently, inertial sensors, or IMUs. Researchers also investigated internal load measures to quantify the effect of this load, such as RPE, heart rate response, neuromuscular function, biochemical response, hormonal functions, various questionnaires, as well as tracking sleep quality and quantity. At present, no single definitive marker exists, so the application of monitoring systems continues to be a blend of art and science. I am focused on using the available technology to develop a mechanical load sensing system for the challenging military environment and ultimately contributing to higher rates of operational availability. I believe the most important features of any load monitoring system are that the metrics are based on first principles physics. They start directly at the accepted laws of physics. This gives them tangible value. Metrics are both broad, covering as much of the movement spectrum as possible, and compiled. They are able to be broken down into their composite components when required to bring context to mechanical load and facilitate deeper insight. They should provide results that are both absolute and relative, accounting for the changes in performance that accompany changes in body mass. They should also employ a zonal system to classify sessions, days, weeks, or longer periods into zones, such as from very light to very heavy, based on the premise that an optimal zone exists for physical load that relates closely to an individual's previous training history, current physical status, and injury risk profile. The last 2 points on this slide are the most important when it comes to creating changes in group behavior. The metrics must be easily understood and encourage conversations using a common language. If accurate and easily understood outcomes are provided by a monitoring system, this can result in improving the understanding of training responses, assisting in the design of better training programs, enhancing the communication between stakeholders, and improving an individual's performance. I will now briefly cover the following points relating to this project. The Vicon Blue Trident sensors were selected based on their durability and ease of use, as well as the strong reputation of the Vicon brand in biomechanics and technology. The 9-axis sensors incorporate 2 accelerometers sampling at up to 1,600 readings per second, a gyroscope at up to 1,125 readings per second, and a magnetometer at 100 readings per second. They are waterproof, shockproof, and are simple to operate and apply. Their dimensions are 42 by 27 by 11 millimeters with a mass of only 9.5 grams and a battery life of 12 hours with current firmware. At present, 20 sensors have been used for data capture, downsampled to 225 readings per second to balance granularity and file size. In this project, the devices are positioned anteriorly at the level of the belt buckle, as this location is both unobtrusive to physical activity and as close to the human center of gravity as possible. Two different belt types have been used, a modified polar heart rate belt for rehab and PT use, and a rugged Velcro belt for operational activity. During this development phase, it is vital to understand the IMU axial alignment given the device orientation. The three axes of the accelerometer have been abbreviated to AX, AY, and AZ. AX relating to the lateral axis, capturing accelerations from side to side. AY relating to the vertical axis, capturing up and down acceleration. And AZ relating to the frontal axis, capturing forward and backward accelerations, all measured in meters per second per second. The three axes of the gyroscope have been abbreviated to GX, GY, and GZ. Classically, axial rotations are termed pitch, yaw, and roll, and are measured in degrees per second. GX once again relates to the lateral axis, but records rotational velocity forward and backward, or pitch. GY relates to the vertical axis, but records twisting velocity, or yaw, whilst GZ relates to the frontal axis, recording tilting from side to side, or roll. The data capture process has thus far included the development of an appropriate exercise battery covering as much of the physical spectrum as possible, structured and annotated capture of these exercises, including 2 participants to test the efficacy of the approach, 6 participants with accompanying GPS data to provide a speed trace to act as supervision for the ambulatory algorithms and investigate the differences between individuals, 20 military participants performing the same exercise battery to provide a training data set, a 20-kilometre pack march at best pace to more deeply investigate the relationship between performance, mechanical efficiency, and fatigue, as well as unstructured training exercises in an urban environment to mimic a random, real-world situation. Additional data capture has more recently been performed on inclined terrain, with and without load carriage, to investigate the accuracy of predicting terrain incline and speed during ambulatory movement. Future data capture will be focused on increasingly unstructured military activity in real-world settings. Here is a representation of the current data pipeline and modelling processes. Raw data is imported into the pipeline at 225 Hz in CSV format, involving Unix timestamps, 3 accelerometry axes, and 3 gyroscope axes. The data is checked for missing values and gets fed in ready for processing. Initial feature engineering involves adding calculations and combined columns to the data that will be used in the modelling stage to assist with detection of different modes of movement. Multiple classification models based on gradient-boosted decision trees are used. The raw IMU data is grouped into 1-second blocks, with aggregate features added as inputs for the training models. The model has been run on a random stratified 80-20 split, where 80% of the data is used to train the model and 20% is used to test the model. The data goes through a model hierarchy, where each model adds features that act as inputs for the subsequent models. The order of the models is ambulatory, class, category, and exercise, with the overall goal being to classify which exercise the 1-second block of data most likely belongs to. Post-feature engineering refers to the creation of extra columns after the models have been run. These are features that can only be made after the models have been applied, as they require information from those models. For example, the model can only do step counts after the ambulatory model has been run, which detects and separates ambulatory movement. Data output is to a CSV file, ready for dashboards and visualizations. The data is bucketed into exercises so that different algorithms can be applied to each exercise to count the number of repetitions performed. I will now summarize the current data science statistics for the models and discuss some of the insights thus far. In data science, statistics are used to explain the performance of machine learning models. Commonly used measures include accuracy, precision, recall, and F1 score. The 4 conditions that affect these statistics are true positive, when the model decided that an exercise occurred and the exercise actually did occur. This is good. True negative, when the model decided that an exercise did not occur and the exercise actually did not occur. This is also good. False positive, when the model decided that an exercise did occur, but the exercise actually did not occur, a false alarm. And false negative, when the model decided that an exercise did not occur, but the exercise actually did occur. We missed it. Accuracy is perhaps the most intuitive statistic and is equal to how many guesses the model got right. Precision is equal to how many rows of the exercise data we predicted were actually exercise data. Recall or sensitivity relates to, of all the actual exercise data, how much of it did the model correctly predict. F1 score considers both precision and recall and represents the average of these two measures. Here is a graphical representation of the current accuracy statistic for each of the four models. 96% of ambulatory data guesses are correct. 98% of the guesses are correct for class separation of ambulatory data, assault movements, body weight training, cardio equipment, strength training, and swimming. 96% of the guesses are correct for separating exercises based on load carriage. Category 1, no additional load. Category 2, assault order load carriage. And Category 3, operational order load carriage. Finally, an average of 98% of the guesses are correct for identifying individual exercises following the input of data from the previous three models. Here is a graphical representation of additional data science statistics for the exercise model detecting 32 different exercises. It can be seen that many of the exercises are above 90% for precision, recall, and F1 score, which is very promising. The exercise model is currently having the most difficulty with some of the strength, cardio, and assault movements, which is likely related to the proportionally smaller data set for these exercises, as well as the shorter duration of some of these movements. Ongoing work is being done to further refine these algorithms and improve detection accuracy. The practical implications and relevance of a mechanical load sensing model for a military population is that it improves the understanding of workloads of the individual outside of structured PT. It also provides an objective way of analysing the mechanical load of military training courses. It informs the rehabilitation of injured personnel to assist in improving outcomes and supports performance optimisation, career longevity, and mitigation of injury risk. This example shows summarised minute-to-minute data from a 20-kilometre pack march at best pace. The orange trend line shows the change in step rate per minute across the 3-hour time period. This participant can be seen employing a pacing strategy, presumably to optimise movement speed and manage fatigue, involving cycling between shuffling for a short period at approximately 150 to 160 steps per minute and walking for a short period at approximately 120 steps per minute. The blue trend line shows the change in average resultant acceleration. This can be seen to increase throughout the march, despite a somewhat consistent average step rate overall, perhaps indicative of mechanical inefficiency due to increasing fatigue. This graph involves the same individual showing average vertical peak of each step, left in blue and right in orange. It also shows the vertical peak symmetry across the duration of the march in red as a 15-minute moving average, displaying the change in step symmetry throughout the activity. A large asymmetry develops that involves the left steps registering approximately 5% higher vertical peak impacts than the right steps by the end of the activity. This presumably was due to pain and/or fatigue causing the participant to adopt a compensatory ambulatory strategy. This pattern is very similar to the changes in symmetry I have seen as injuries develop in professional athletes. The measurement of the longitudinal change in gait symmetry will form an important component of the overall monitoring system and complements the measurement of mechanical load. It provides valuable insight into the gait, which can be used to assist in mitigating the risk of injury. These 4 points have currently been prioritised as the most relevant next steps for the project. 1. Improving generalization of the models, which explains the ability to classify data that hasn't been used during the model training phase. Currently, there are some problems when the model attempts to assess new data sets that look different to the data that was used to train the model. Increased flexibility in temporal features is showing promise in this area. Expansion of step metrics to include contact time, flight time, swing time, and dual contact phase are dependent on the accurate determination of both initial contact, IC, and final contact, FC. These metrics will be very sensitive to changes in gait strategies. 3. Development of a mechanical loading framework based on first principles metrics follows on from the last point. Generating loading parameters and zones will be based on standard benchmark activities or physical tests. In professional sport, these zones are related to match loads. 4. Delivery of a user interface that clearly communicates the findings to all stakeholders using a standard reporting structure that enables stakeholder insight. Thank you for the opportunity. I am happy to answer any questions.
Thank you, Andrew. Still no questions coming through at the moment. I believe Andrew is on the line. So I've got a question, Andrew. You mentioned, so the model seemed really accurate for the exercise that you've tested. And you mentioned that, I guess one of the next steps would be to look at more sort of unstructured type of exercise patterns. Could you sort of elaborate what that means and how confident you would be based on the data you've got that the models will be accurate for that kind of exercise as well?
Yeah, thanks, Spencer. At present, we believe it's overfitting a little bit to the exercise, to the training data that we have. So, the methods we're using there are basically to trial different types of models, but focusing mostly on temporal features to do with overlapping windows, things that can provide an understanding of changes in repetition rate, stride rate, exercise rate, those sorts of things, and compiling a better test set. We do have an urban activity as a good test set, but also looking to reproduce the exercise battery as a completely separate test set. And that's the main focus at the moment, is improving the generalization.
Thank you, Andrew. We've got one question coming through the Q&A. Are you planning, asked by Eugene, are you planning to use sensors other than accelerometers?
At present, the model is using the triaxial accelerometer and the triaxial gyroscope. We don't have any use for the magnetometer data at the moment, which is inside the file, but are investigating the efficacy of including the quaternion data, which is in there. So that's a feature at the moment, is trying to include the quaternion data into the models, as we do think that will help with some of the generalization issues that we've seen. The results that I showed there are using 3 axes of the accelerometer and 3 axes of the gyro. Eugene?
Thank you, Andrew. Well, I think that might do it for you. So thank you for your time. We'll move on now to our second presentation. So we have Samantha Betts, who'll be presenting the use of wearable technology in the evaluation of gait patterns of soldiers during weighted locomotion. So thank you, Samantha. Just bear with us. We're just getting the pre-recording ready to come through.
Hello, my name is Samantha Betts, and welcome to this presentation that will discuss the use of wearable technology to evaluate gait variability within soldiers during weight-loaded marching. In 2000, the ADF produced a health status report that demonstrated that 67% of soldiers within the Australian Army had received an injury directly related to weight-loaded marching. I joined the Australian Army in 2013, and during my time at the 1st Recruit Training Battalion, I, like many others, received a lower limb injury directly related to weight-loaded marching. Unfortunately, musculoskeletal injuries remain a major problem within the Australian Army. These injuries detract from mission readiness and prevent soldiers from deploying, which can cause a high financial burden on the organisation. An effective military requires individuals to be agile, effective, sustainable, and lethal. However, injuries can detract from the overall capability and will interrupt individuals' active duty. Approximately 60% of lower limb injuries and 27% of lower back injuries are caused by weight-loaded marching. This can vary from a small blister to severe nerve or bone injuries. Marching is a fundamental skill for military during training and on deployment. If a musculoskeletal injury is sustained during a hostile conflict whilst wearing any degree of external load, there is a significant impact not only on the individual who has been injured, but all those who attempt a rescue mission. Okay, as previously mentioned, weight-loaded marching is a fundamental locomotion skill within Defence Force. So soldiers may be required to carry protective, sustainment, and mission success items which can weigh up to 50 kilos. Whilst performing these combat tasks, it's usually unpredictable and hostile environments. The mission tasks can often alter in time, so often soldiers will be carrying this excessive weight for extended periods of time. So military typically tend to march in one of three states. So patrol order, which is about 10 kilos, fighting order is about 30 kilos, and marching order is about 50 kilos. And these weights are often determined by the task required of them and the equipment that is supplied to them, depending on their core and their mission task. And generally, as a minimum, soldiers will be wearing webbing, body armor, helmet, and depending on where they're moving, a pack. Currently, limitations regarding this topic in assessment of gait have occurred under closed conditions, generally in laboratories, which loses its external validity. For example, using retroreflective motion analysis like Vicon, after the placement of reflectors, immediately takes away all aspects of task-specific performances. The data limitations and the post-processing is quite huge, and the time from data collection to feedback, again, is quite a significant period of time. And you're only able to collect one person per time, and this just would not work for defence. Currently, no motion analysis tools are able to detect gait during task-specific performance to determine combat capabilities. The aim of this study is to assess the gait biomechanics of Australian soldiers during task-specific loaded marching performance conditions. So the objectives of this, firstly, will be to explore the efficacy of wearable sensors in detecting the gait variations, and secondly, to determine the variations to gait biomechanics with different loaded marching conditions. So the participants for the study were those posted to Swartz Barracks in Oakey in Queensland. The ranges for this were 18 to 55 years old. The participants were required to hold a medical classification of J11 to J23 and hold no permanent restrictions that would prevent them from participating. They were also required to be regularly participating in physical training. Those that met the criteria were given a brief summary of the study. And from this, they were asked to sign a consent form and fill out a PARQ form. So the study testing protocol was conducted weighted and unweighted. A single sensor was placed on the lower back at L5 and S1. The sensor was placed on with a single strap of Coband, which was single use as per our COVID safety plan. So individuals were asked to march with the tactical tailor pack, which you can see on the right-hand side there. And what happened was we placed 1 kilo weight inserts and we spread them proportionally over the pack, and that weighed a total of 35 kilos. The pack also consisted of an Alice frame, and what this did was it allowed the sensor to sit at the same spot, so the L5S1, but the pack would sit off of it. So we had the, so it reduced any interference or anything like that. We conducted some video footage of each trial, and this was just for a reference. So the participants were asked to march for 1 minute continuously for each of the weighted and unweighted conditions.
My name's Jim. I'm taking over for Samantha for the next few slides and talking about how we analyse the data and so forth. So the assessment that we carried out, we made sure that it was under task-specific performance conditions, specifically that it was typical of what soldiers wore and performed in marching situations. So in an unloaded situation, in a loaded situation. We did this by using wearable sensors, and we looked at the gait kinematics of the walking, which was specifically the temporal kinematics, so the timing of steps, and also for the magnitudes of when the heel strike occurred. We did this in the Y direction, so the vertical direction, as you can see on the bottom right-hand corner there of the diagram with the sensor. So that vertical acceleration is is the only data that we did look at. At this point in time, we are looking at more data, but reporting here, this is all we're looking at. We extracted the data from the sensors using our custom designed STEMkit toolbox. And from that, we were able to pull out that vertical data, the x-axis data. And we looked at the temporal measures of heel strike to heel strike for the timing of the step and also the magnitude of that vertical acceleration. Like what I said, we compared the situations of unloaded and loaded situations, and we used the paired features to make a comparison between the two. So here's the diagram of the extracted data of the unweighted march, and this is typical of one soldier for about 40 or 50 steps. You can see there the magnitude that the peaks were slightly less on average, slightly less than 1.5 Gs. And for this data, for this particular person was 1.43 from memory Gs, was the average of each of those peaks. Moving on to the next slide, you'll see a variation in that. So here's the weighted results, and you can see that the peaks are certainly less than the 1.5 G that you can see on the left-hand side on the y-axis. And these averaged slightly under 1.2 G. So there was considerable distance and a significant difference when analysed on the magnitudes of the data. The step timing was taken between the peaks of these, and there was shown to be no significant difference between the step timing. The next slide will be able to describe or visually display that a little bit more effectively. Okay, this is the Y acceleration data of both the loaded and unloaded situations. It is the raw data that's come out of the device. So you can see on the Y-axis that it is still measured in millivolts rather than being converted to Gs. We've depicted it this way because it displays it a little bit more effectively rather than with using the STEMkit data that's been extracted that way. But you can see here that the orange data, the orange time series that's the unweighted data, and you can see that that is significantly more than the weighted data, which is the blue. The temporal measures you can see as well is that they are much similar, a little bit of variation, but not a lot of variation, and that there was no statistical variation there, which is indicating that the soldiers are conditioned to march at a specific timing of their stride time, which would be understandable. Okay, so what does all this mean? It means that the wearable sensors detected the kinematics of the gait, and it has shown what's been reported by other people, that there's no real variability in step timing, but there were significant variations in the vertical acceleration of the data. So this indicates that we can monitor with the sensors, or it can be monitored with the sensors, task-specific conditions. And so we can drill right into what's going on with each individual who wears one of these devices. This may mean that we can lead to early intervention to prevent injury if we can see changes in gait profile or data like that. Like what I was saying there before, we are looking at the other data. Because of the timing and everything, we haven't been able to run the analysis on the anterior-posterior data, but that looks also significant. If you want to know about that, please ask questions afterwards. Back over to Sam.
Weight loading changes gait biomechanics. The gait biomechanics changing is not unrealistic. This is because of the task-specific gait requirements. So, for example, if we look at the gait biomechanics of a rugby league player, if we place a ball in his arms and ask him to run, his gait biomechanics will be completely different to, let's say, a sprinter just sprinting. So by simply placing a pack on someone's back, the biomechanics will change. This demonstrates the importance of preparing soldiers for combat through task-specific training. Otherwise, altered biomechanics can lead to possible injury. Okay, so what does training look like then? So the training needs to be more specific. Train like it's actually combat. So these sensors will enable close observation to start engaging the neuromuscular changes and metabolic adaptations to enable soldiers to properly prepare. The sensors can also train to become more individualized, managing workloads depending on the sensor feedback and working towards a more combat capable soldier. So if we look at working with a whole platoon, we can receive individual feedback and work within that individual's physiological demands to significantly improve the overall progression. As I progress into my PhD, we will look more directly at the longitudinal examination of locomotion performance under load. We want to build a greater evidence base for why sensors are the way of the future and allowing for a strong conclusion for their implementation into this organisation. Our aim is to develop wearable sensors that will have better detection of gait variability whilst not interfering with performance. And lastly, we aim to work with the engineers to develop software analysis that is able to supply immediate feedback and error detection, and this will allow for immediate correction and ceasing of activities before injury occurs. All right, so just lastly, the take-home messages from this presentation is that weight-loaded marching can change gait biomechanics, which increases the risk of injuries. Wearable sensors can detect locomotion biomechanics under load, and this is proving to be fundamental in observing soldiers in task-specific performances. And this enables us to have a greater understanding of a combat-capable soldier. And lastly, we're just leading into the importance of understanding the predictors for injuries within soldiers to keep our soldiers safe. I look forward to working with a courageous team to implement and change current practices within the Australian Defence Force, to improve soldiers' performance, and most importantly, to keep our soldiers safe. So please feel free to reach out to me with any comments or questions. Thank you very much.
Thank you, Samantha and Jim. Please post your questions if you have any. We have one that's come through. I think we've got Jim on the line to answer these. So if you did this again, this is coming from Phil, sorry. If you did this again, would you use Coban to secure the sensors? It's very loose fitting material. Was there a lot of noise in your data?
There was noise in the data. It's probably an area that we would investigate on the efficacy of sensor attachments as such. Going back to previous research that a PhD student of mine has done previously of validating and comparing skin-mounted sensors to tight clothing to loose clothing. Tight-fitting clothing, tight belts and so forth, there's very little difference. There was trivial difference between the data, but with loose clothing, there is certainly artifact there that needs to be addressed. And it's outside the scope of what Samantha had done here, but it's certainly something that we would have to look at moving forward.
Thank you, Jim. Another question, automatic skill execution tends to break down with immediate feedback. Are you planning to account for that?
Sorry, could you just repeat the question again? I was just a little bit distracted, sorry.
Sure. Automatic skill execution tends to break down with immediate feedback. Are you planning to account for that?
Again, it would be something that we would investigate at the needs of being able to look at all situations. Again, other research that we've done in other areas, we've looked at the development of the technology to give immediate feedback delayed feedback, the way the feedback is given, in a visual sense, in an instantaneous sense. Again, like what I said, it would be processes that would be implemented in the future research to see what would be required. Because in assessments, what we do need to do is provide a product that is worthwhile to the individual, the soldiers, and to the military themselves. So if we're going to go down that pathway, we have to make sure that what we give is appropriate. And so all those variables would have to be looked at for sure.
Thanks, Jim. We've got a few more questions coming in, which is good. So Emma's asked, did you link the gait variability to injury rates in this study?
No, we have not. At this, we were looking at personnel, the volunteers, to make sure that they were not susceptible to injury or had injury that would affect their gait at this point in time. We want to use it as a tool to be able to either be a predictor of injury and changes of gait, and we've seen that previously with where changes just in velocity alone with healthy participants, that just a change in velocity will alter gait patterns. So injury should present itself early on or early onset of injury, and so soldiers that can be detected, and therefore soldiers can be pulled up before the onset of major injury or a major onset of injury. And so that's part of the objective of what we're attempting to do.
Great. And so you didn't collect data on injury for this particular study?
No, only what was said in the literature review of the individuals. It was just that they had to be injury-free in the period of time. From memory, 12 months. I stand to be corrected, but injury-free in the 12 months leading up to the data collection.
Sure. So Bevan, I think your question was linked to the previous one, so I think that answers your question as well. Well, thank you, Jim and Samantha. We'll move on now to our next presentation, and that is from Danielle Vickery-Howe. And this is a pre-recorded presentation as well. Are there kinematic sex differences across the gait cycle during overground load carriage? Thank you, Danielle.
Good day all, my name is Danielle and I'll be presenting research comparing kinematic sex differences across the gait cycle during load carriage. Load carriage is a universal soldiering task and a requirement to carry the necessities such as clothing, protective ensemble, combat equipment and sustainment stores. Through history, the amount of load that soldiers have been required to carry has increased as auxiliary transport was de-emphasised and supplies and equipment had to be carried on foot. Biomechanical research is undertaken to develop general principles of the most efficient and safe ways to carry load. Over time, many different factors have been studied, and there is not one perfect fit for all soldiers in every condition. Different factors relating to the load itself that have been explored are the variation of load, including different distributions, integrating systems such as a pack frame, hip belt and straps, and the placement of load within the pack, and the effect of load carriage as it moves away from the centre of mass on the feet, thighs and hands. Other factors can include the effects of different walking speeds, surfaces and environments. The removal of gender restrictions on many roles has increased the overall participation rate in the Australian Defence Force. In 2013, there was 4.2% female participation, which has grown to 18.6% as of 2019. It is known that females are highly represented in health and logistical roles, but there has been increases in the proportion of women in all occupational groups. So gender restrictions to all roles, including combat roles, have been removed from numerous armed forces. The common load to be carried by Australian soldiers is 23 kilograms, but can be up to 35 to 40 kilograms for those combat roles. And combat roles are known for their higher work rate overall, the requirement to march for longer, carrying heavy loads, and have specific tactical skills and knowledge. So there's now the potential for females to be more frequently exposed to heavy military load carriage. So we know loads are vital for protection and sustainment, but they can cause occupational injuries. So females commonly have greater incidence of injuries when compared with males in general exposure. In Australia, when looking specifically at load carriage injury rates prior to those removal of restrictions to the combat roles, females were at twice the level of suffering a serious load carriage injury and of suffering foot injuries when compared to males. So the back was the most common site of injury for both males and females, and other common sites were the ankle, knee, and the neck and shoulder complex. So the possible reasons as to why females have a greater injury risk may be the fact that the mass carried relative to body mass is greater than in their male counterparts, and this will then cause female soldiers to work at a higher percentage of their VO2 max and have greater metabolic stress to perform the same given task. And finally, the fit of soldiers' equipment is reported to be more problematic for females in terms of their size, shoulder straps, and stability of the actual pack itself. And this would then increase overall total musculoskeletal discomfort and then interfere with their task performance. Between 0 and 40% of body mass, spatiotemporally, females have been found to have no difference to males or walk at faster cadences and shorter stance times in participant samples representative of a recruit with age and fitness. So females tend to be shorter than males, and it is proposed that the differences that have been seen in the previous studies could be showing a height effect rather than the effect of sex. But when we focus on kinematics, these are largely the same across sexes for the lower limb, and the only difference previously found was at the trunk, for trunk lean, being 2 degrees greater in females when carrying a 22 kilogram load. So there have been no differences found for lower limb peak joint angles between males and females, but the limitation of these previous findings is they have only reported or compared the peak angle for the given joint. This limit means it only looks at one discrete time point over the entire gait cycle. So further insight may be provided if we can investigate the relationship between load and sex across the entire gait cycle. Therefore, the aims of this study were to investigate the interaction between sex and load on lower limb kinematics across the gait cycle during overground load carriage. So we had a total of 30 participants for this study, both male and female, all were injury-free for at least 6 months and met the Australian Army entry physical fitness requirements. Additionally, all participants were load carriage naive, therefore representative of a recruit. The protocol consisted of 3 by 10-minute walking trials with 10 minutes of rest between each bout. The participants carried 3 different loads, 0, 20, and 40% of body mass. Loads were distributed evenly between front and back and incremental to ensure safety with completion of the task. Walking speeds were self-selected and determined prior to testing in order to maintain it via stopwatch during the trials. A total of 36 retroreflective markers were attached to each participant's pelvis and lower limbs, and a 10-camera Vicon motion capture system was used to track marker trajectories. Raw trajectory data were filtered using a low-pass Butterworth filter at 6 Hz, and a lower body direct kinematic model was used to calculate sagittal plane joint kinematics for the hip, knee, and ankle. Kinematics were then time normalized to the entire gait cycle, so from 0 to 100%. Statistical parametric mapping, or SPM, was then utilized to make those statistical inferences regarding this time normalized data. Two-way analysis of variance with repeated measures on one factor using SPM were conducted to assess the interaction between sex and load across the gait cycle. And where these significant interactions or main effects were present, SPM two-tailed paired t-tests were conducted to determine the location of that specific difference, with our p-value set at less than 0.01. The following 3 slides will have the same figure orientation. Figures 3 through 5 show the results from the ANOVA of the interaction effect between sex and load for each joint, the ankle, knee, and hip from left to right. So each graph has the SPM F value on the y-axis and from 0 to 100% of the gait cycle on the x-axis. The red dashed line represents the critical F value for an alpha level of 0.01, and that black solid line is the result of interest. So for our interactions, there were no significant interactions for any lower limb kinematic variables. With the same orientation as the previous slide, there was also no significant main effect for sex for any of our kinematic variables. There was, however, a significant main effect for load for all kinematic variables. So at the ankle, there was a main effect for load between approximately 50 to 63% of the gait cycle. For the knee, there was a main effect for load between 6 and 13%, 45 and 64%, and from 92% to the end of the gait cycle. And at the hip, there was a main effect for load between 18 and 44% of the gait cycle. As there was a main effect for load at each joint, paired t-tests were run to determine the location of the difference for each loading combination. The top row of figures show the mean and standard deviation for the pairwise comparison. The y-axis is hip flexion or extension in degrees, and the x-axis is the percentage of the gait cycle. The vertical dashed line with the shade indicates the area of significance based off the pairwise comparison, and the lines within the graph represent the loading condition. So the black line represents 0% of body mass, red 20% of body mass, and blue is 40% of body mass. And so there is a key in the top right corner if you do need to refer to it. The bottom row of figures are the results from the pairwise comparison with the SPM t-value on the y and the gait cycle on the x-axis. So beginning with the hip flexion increased as load increased for 0 to 20% of body mass between 12 to 14% of the gait cycle and from 89% to the end of the gait cycle. There was no significant difference between the 20 and 40% body mass loads, and hip flexion was increased for the 0% to 40% comparison from 20 to 31% of the gait cycle. So this is the same orientation as the previous slide. So black representing 0% body mass, red representing 20%, and blue representing 40%. Looking at the knee joint across all three pairwise comparisons, knee flexion decreased as load increased for each loading condition from approximately 46 to 64% of the gait cycle, and this is through pre-swing and toe-off. And knee flexion increased as load increased later in the gait cycle for 0 to 20% of body mass from 70 to 79% of the gait cycle, and for the 0 and 40% comparison from 93% to the end of the gait cycle. Ankle dorsiflexion increased as load increased from the 0 to 20% body mass comparison and the 0 to 40% body mass comparison from approximately 50 to 63% of the gait cycle, similarly to the knee during pre-swing and toe-off, but there was no difference for the 20% to 40% body mass comparison. The results demonstrate that lower limb kinematics are similar across the gait cycle between men and women carrying loads up to 40% of body mass at a self-selected walking speed. The response to load is the same across sex and is not dependent on either factor. And this is in agreement to previous literature where relative and absolute loads were carried. It is interesting to note, though, that previously Krapenovich and colleagues had hypothesized and saw a significant gender by load interaction through stance for average trunk position, where females had an increase in approximately 13 degrees in forward trunk flexion, whereas males only exhibited an 11-degree increase. So this was not investigated in the current study. However, it would be interesting to include this in a future research design. So the lack of sex difference may indicate that females, who are typically smaller than males, may not adequately compensate for the additional load, and this may explain the increased incidence of lower limb stress fracture injuries when compared to males. Our results show the proximal joint, the hip joint, is the one that increases at the beginning of the gait cycle, at foot flat and mid-stance. This may mean that you step slower as the load increases, so you have more time with the body centre of mass over your supporting leg, presumably to assist with absorption of ground reaction forces. And this is partially in agreement with previous literature. So studies have shown that increasing a pack-borne load also increases these peak angles at the hip. However, when load is evenly distributed, there is not commonly the increase in peak hip flexion angles. Through pre-swing and toe-off, the distal joints, so the knee and the ankle, are more extended or plantar flexed when load increases. This could be to assist with push-up to propel the body forward with that increased additional load. Increasing range of motion does make sense here to have their foot on the ground for longer during each stride to increase stability. Preparation for heel strike during terminal swing may predominantly be controlled by the knee musculature, so increased flexion, rather than at the ankle where we saw a decrease in plantar flexion. So this may allow for more muscle activation upon heel strike to support the added load. So previous studies have shown the knee and ankle does not respond consistently with the addition of load and is quite dependent on that configuration, walking speed, and load carrying experience. So the limitations of the previous work start to become clear when results are presented in this way. So reporting of peak flexion extension angles is only looking at one specific point in time. There may be more than one point of difference for a given joint. And as we can see in our data set, there can be numerous differences between loading conditions and they may not always be at the peak. So these differences are seen at mid-stand, toe-off, and terminal swing. And when limited to reporting the peaks, you may only receive part of the story. It is well known that energy expenditure increases during load carriage, and this can result from many factors, one of which being increased muscle activity. So with increased load, activation of the knee and ankle musculature is known to increase for both backpack and vest-borne loads, likely to control for that weight acceptance and propulsion of the body. So this increased muscle activity results in greater demand for oxygen to the muscle, therefore increased energy expenditure and physiological demand overall, and faster time to fatigue. And fatigue is known to have an effect on gait completely separately and would be of interest to study in the future. In conclusion, there are no sex differences in kinematics up to 40% of body mass in healthy recruit level adults, up to 10 minutes. However, this may mean that females and males who are shorter may not adequately be compensating for this external load and may explain the increased incidence of lower limb injuries. Increasing in joint flexion angles around heel strike and extending the knee leading up to toe off will likely then result in increased muscle activation and physiological demand. So the results of our study that aim to quantify the biomechanical movements during load carriage can provide an increased understanding of the biomechanical responses to load carriage in general and between sexes. This can facilitate improved load carriage conditioning and task management and help to mitigate injury risk overall. These outcomes will ultimately have the aim of reducing the number of working days lost to injury or disability in both recruits and active duty soldiers. A future direction to explore is absolute loads, so the removal of confounding factors such as body mass and physical size by carrying the relative load and walking at a self-selected walking speed did allow the current investigation to analyse sex differences during load carriage, but this does not reflect the typical practice in a military setting. So it is likely when comparing grade to absolute loads and walking speeds, sex differences may manifest. So it would be interesting to see if this is still the case when carrying the heavier loads, such as those carried in combat arms of up to 35 to 40 kilograms. Experience is another interesting variable, so further research is required in that recruit population with no prior load carriage experience to monitor biomechanical adaptations during absolute load carriage through initial recruit training and employment training to gauge how soldiers respond to load with increasing experience. And lastly, future research that investigates the walking mechanics during prolonged load carriage tasks would be ecologically relevant to understand if sex differences become amplified with fatigue and across durations that are greater than 10 minutes. I'd like to thank my co-authors for their contribution during our research project and subsequent outputs, and then thank you all for listening today.
Thank you, Danielle. Interesting study. We have a question. Congratulations on a very thorough study. What difference do you think your results would make to those designing and delivering the training cycle?
Yeah, thanks. That's a really good question. So that's something that I guess will come with, future research. So there has been some previous literature published by Jodie Wills and her research group around what a specific, load carriage conditioning program can do to improve performance. And they've found that with a well-rounded program that you can get improvements over a 10-week training program. So I suppose taking some insight from that and based off what we found where I suppose the knee and the ankle were the most variable when you increase load. They could be, I suppose, the parts of the lower limb that you focus more so on during those early phases of training and throughout the entire recruit training session, I suppose, time cycle, to ensure that they're, I guess, reducing the number of injuries they get throughout their entire, I guess, recruit training cycle.
Yeah, I had a question. Where is it? I've written it somewhere. Yeah, so you mentioned it, as one of the future directions, looking at sort of exercise longer than 10 minutes. Do we know, is the rate of fatigue, does the literature say anything about the rate of fatigue being different between men and women?
I haven't actually looked into that very closely, but I can imagine there would be some difference if females are working at a higher percentage of their VO2 max over, that extended time period. You would assume that they would get fatigued more quickly, but that is definitely something that I would be interested in looking into, and I can obviously get back to you on that if you're interested in having that conversation.
Yeah, great, thank you. I think that's all for that one. So thank you very much, Danielle.
Thank you.
We'll move on now to our next presentation, and we have Douglas Silva Cinzanando. I hope I got that right, Douglas. And he's going to be talking about the impact absorption analysis during the gait wearing 2 military boots with and without load.
Hi, my name is Rodrigo Vini, and I'm here to talk to you through our presentation, which is the impact absorption analysis during the gait wearing of 2 military boots with and without loads. This work has been done in Brazil in partnership with the School of Physical Education of the Brazilian Army and various organizations in Brazil, and with collaboration with us at La Trobe here in Bendigo. So the topics of the presentation will involve a brief introduction and background, some research questions, methods, results discussion, take-home messages, and future research that we are planning to do or that we are already doing. So a bit of a very brief background. So main types of injuries. So we sort of have 2 main types of injuries that we are more used to come across. So the first one is obviously acute or traumatic injuries, and you've got an example there of a football player which has been hit on the ankle. So that is an acute injury, which means very large amounts of force over a very short period of time, which normally exceeds the threshold for the tissues, and then we've got a rupture on the soft, sometimes even hard tissues as well. And we also have chronic or non-traumatic injuries, which have a bit of a different mechanism related with. One example is the chondromalacia patellai, which has been called as the runner's knee. So not an excessive amount of load, a moderate amount of load, but apply for a very long period of time, which means the tissue doesn't have sufficient time for recovery and gets into a fatigue mechanism. When we look at the response in terms of a tissue loading, what we tend to see is that the chronic or non-traumatic injuries, they are just above the physiological loading, which means we just in the borderline between a physiological loading and injury, which is what we call a little bit of a microfailure, sort of range between load and the displacement or the strain of the tissue, or the changing length of the tissue, which then means we just have to try to bear in mind on how that magnitude of the loads accumulated over time actually leads to the development of injuries. When we look at injuries in the defense force, what we tend to see is that the incidence is quite varied, so somewhere between 2 and 46%, but 76% of those are non-traumatic, which means we're not really talking about the ankle sprains here, we're talking about those injuries that develop over time as the large bulk of injuries. The types of injuries are varied as well, so they can range from stress fractures to anterior knee injuries to low back pain and others. So those are just the more often. The cost of injuries are pretty substantial because we talk about 71% of the health-related sick leaves are related with injuries, which that's data from the New Zealand Defence Force. And data from the Australian Defence Force seem to indicate that 48% of those injuries, health-related injuries, happen during physical activity and exercise. So which means that the the engagement of the defense personnel in physical activity is quite important, and that sometimes leads to injuries. And some of the risk factors that have been identified in the systematic review that we are referring here are large running training volumes, rapid increases in training load and loaded activities. So performing activities with external load is quite important for the defense force, but also increases the risk of injuries. And as you can see on the graph on the right side of the slide, you can see that the load actually increases almost like linearly with the percentage of activities involved in operational tasks, which means when defense personnel actually have to do operational tasks, they normally have loads involved on that. So either carrying backpacks with heavy load for a very long period of time or handling other large volume of objects. So that's an important thing as well. Shoes. So the boots that I used are quite embedded on the process as well, and the shoe mass seems to be quite important because we're not talking about sports shoes, right, which are low mass, quite flexible depending on the design, but we talk about a heavy boot that adds on that external load, right? And it seems that the addition of load actually increases the energy expenditure and reduces efficiency. So the lighter the load, the less efficient becomes the movement pattern. That has been largely studied on particularly running, but it also influences gait patterns as well, as we can see on this on the systematic review that we are looking at in this slide. So we've done a study some years ago, and then we compared some designs of boots. There are many out there, but we compared 3 boots. So one that has a bit thicker midsole, is built in from rubber midsole, reasonably thick, reasonably heavy as well, so around the 600 grams of mass. Some intermediate design, as you can see in the center, which is again rubber-based midsole with a bit thinner midsole and probably not as heavy in terms of overall mass, and another one which is more a commercial design, a bit thicker again, so a thick midsole, but built from different type of material, so polyurethane, and then lighter, so a lighter midsole. And what we observed is the lighter midsole seems to be more comfortable for defense personnel, so people that are normally used to use those boots in their regular operation and working tasks. And the heavier midsole, the heavier boot was obviously not as comfortable, but reduced impact to a greater extent. So but the problem is how does boots actually respond to the external load? So how we marry up the load that you carry in your operations and the design of the boot. Do they respond similarly? Because there's the study that I referred just before hasn't looked at that because we were just looking at people without external load. But the question would be how those boots actually respond to the addition of load as well. So what we've done to answer that particular question, we recruited 28 soldiers. They were reasonably young, and they walked over a 10-meter walkway with 2 force plates embedded on that. And basically, we had a randomized order in order to sort of randomize the loads and the boots in a way that the order effect wouldn't influence the results. And obviously, we used a backpack with sand filled up to 15 kilograms. We also did mechanical testings with the boots. So we sent them off to an accredited lab, which has years of experience on assessing the mechanical properties of the load. So they identified, so they measured the mass, they've measured the energy absorption, as you can see on the screen, the Shaw A, which is a measure of hardness of materials, density, midsole material, and then we were able to actually separate the 2 boots that we were looking at. So a lighter boot and a heavier boot, and how they are different in terms of the design. So very similar in terms of, quite fairly similar in terms of midsole and the insole thickness, which was one thing that we wanted to improve from the study that we've done before, but largely different in terms of energy absorption, Shaw A, and mass. So key measures that we extracted from the data, we obviously look at vertical ground reaction force, which is sort of a standard way to assess impact whilst walking. So we looked at the first and the second peak, the instantaneous and the average loading rate, which are responses related to how quickly actually the loads transfer through the body. And we looked at the median frequency, which then give us a sense of whether you've got high impacts traveling through the system as well. We obviously did statistical analysis to compare using a two-way with repeat measures, so boots and load as factors, and pairwise comparison. And then you can see on the screen sort of the points in time over the gait cycle where each of the outcomes is related to. Key results. So as you can see on the screen, the load actually increased vertical average loading rate, which means more load actually led to greater average loading rate, but not instantaneous loading rate or median frequency. So there was a bit of an initial response on that sense. The heavier rubber-based shoe presented less median frequency, which suggests better cushioning. But there were no differences between shoes during the loaded walking, which means the response was probably quite similar between shoes. So the increased impact during loaded walking in line with prior research was observed here, which means as you walk with an external load, you got more impact. So there's more load coming from the ground, which makes sense and it was expected. And those two studies that we are referring there, they suggested that greater ground reaction force increased the risk of injury, which means walking with external load actually increased your risk of injury, which has been associated particularly with stress fractures, not only stress fractures, but it has been observed in a range of activities, including sports and occupational. The heavier boot with a rubber midsole led to less median frequency. So somehow the heavier boot with the rubber midsole actually worked better for cushioning. And that was interesting because it was a heavier shoe, probably looking back into the study that we've done before, probably not as comfortable as the lighter boot, but potentially better in terms of cushioning, which then reduces the risk of injuries in ways. But the more compliant material was presented less mass and probably not as good cushioning property as the heavier boot. And obviously the heavier boot has been historically associated with greater ground reaction forces, which, and this study has observed that working boots actually tend to lead to greater ground reaction force compared to, for example, running shoes, and we've mentioned that before in sort of expected in ways. The additional mass that you have to carry on whilst you're walking actually increases the forces that you are receiving back from the ground as a reaction. There were no differences though between shoes during loaded walking. So it's possible that we were too conservative in the magnitude of the external load, so 15 kilograms may not be sufficient to actually elicit changes or sufficient changes in the, so we probably would need to do a follow-up study looking at greater loads on the backpack and implications from movement pattern. This study we also analyze, obviously we can't report here because it's we wouldn't have the time to report everything, but we had motion pattern analyzed, and it seems that there is a greater inclination of the torso, which means there are changes in the movement pattern, even with a 15 kilograms load, but those changes are not sufficient to reflect into differences between shoes using this particular load, which means both boots actually respond quite similar, but the body actually compensates and changes its pattern due to that particular load. So take-home message is that, or some of the take-home messages are that 15 kilograms of load increased impact when walking compared to no load, which was sort of expected. The heavier boot with the rubber midsole was better at cushioning than the lighter boot with a PU, which again was sort of in line with the studies that we've done before. But both boots perform quite similarly when 15 kilograms of load was used, which means the better cushioning boot hasn't responded better, or the worse cushioning boot hasn't caught up. So they were still the same magnitude different. And obviously the rubber midsole had less cushioning in another study that we've done, which sort of are conflicting with that one. But we just need to assess potentially different materials to design the midsole of the boots. Just a future research, things that we have already started to look at, and that we are designing and expanding as much as we can, is if we can improve the boots in a way to help reduce injury. So that's one of the key things. We're trying to come up with a innovative material for the midsole in order to reduce the risk of injuries, and that's potentially coming from a composite material, as you can see, like foams built in a plate of different types of material, and we're looking at this stage at materials such as the graphene or carbon fiber. And could these new boots with an improved midsole improve all performance as well, which means can people then walk more efficiently with load with an improved midsole? So that could be great if you could come up with a design of the midsole that would improve energy return, as we have seen in sports shoes, and also reduce the risk of injury. So that's our primary goal in our following up studies that we are just starting. And I would like to thank you all, and just a picture from the city of Greater Bendigo, and I'm happy to address any questions that you may have.
Thank you. That was Rodrigo Bini presenting there. Please post your questions if you have any. Rodrigo is here to answer some. I'll start off. So I think I got this right. There seems to be kind of a trade-off between cushioning and efficiency with the heavier versus lightweight shoes. Do you see, and I know you mentioned some of the sort of future directions there at the end, do you see there being kind of one optimal shoe in the future for all scenarios, or will it be kind of load specific, where you know, kind of like an athlete has, you know, shoes for different conditions or different loads? Do you see that's where it's heading, or what are your thoughts?
Yeah, thanks for the question. I think it's that's something that we have been discussing, because we obviously started probably the other way around. We started planning for the design of the boot in a way that it would improve performance initially, but we are a bit tangled, a bit twisted in the group. So some of us think that that would also help reduce injuries, and some of us are a bit, nah, that probably will lead to more injuries because we will expose people into a greater overall demand in terms of exercise demand. So I don't really know straight from the top of my head which one we are to expect, but we hope that we will be able to get a design of the midsole that will help both things. So that's my hope, but whether I'll be right or wrong, future will tell us.
Yeah. And just another one that comes to mind with all the I guess the attention around the athlete, the marathon running shoes. Have you sort of gained any insight from that technology that the runners are now using? You know, we're seeing world records being broken in the marathon, you know, arguably because of these shoes. Is there any kind of transfer that you can get from that, or that's already been done?
Well, I think the most recent transfer that I've seen is a study, probably has been just published probably a week ago, with the Vaporfly. They've observed the same magnitude of increases from professional runners and recreational runners. So it seems that the shoe also works well with people that run on a slower speed. We're talking still about running. We haven't seen anything on walking, which is probably one of the challenges that we have. Will that design actually work or help people when they walk? And if it does that actually help when they walk with loads, which is probably one of the things that we want to address as a primary aim in the studies that we are, because we're already sort of coming up with the design of the shoe, but we just don't really know what they will land basically.
Yeah, look, it's interesting. I think that's all I had, and there's no other questions coming through. So thank you for your time.
Thank you, not a problem.
Very interesting study. We'll move on now to our next presentation, and this is going to be delivered by Hussein. Sorry, I just lost it off my screen. Hussein Moktazadeh. I apologize again if I've messed that up. And he's going to be talking to us about toward optimal selection of an assistive device to minimize risk of injury and enhancement of performance. So thank you, Hossein.
Thanks, Spencer. Thank you very much for this opportunity. Yes, this is Hossein Mokhtarzadeh, and I would like to thank my co-authors here as well, Kurt, Professor Rizal, and Professor Abdulli. This is part of Physical Assistive Technology Innovation, or PADI project. So I'll be talking quite a lot about assistive devices here and how we can select the optimally select it, basically. So why assistive devices? So we have been talking a lot since morning about performance, about mitigating injury. So whenever we add something to a human body as an assisted device, exoskeletal, or there are a few other names for that, or exosuits, depending on the applications. So these two are basically what we have in mind, at least from biomechanical point of view. We want to improve the performance, reduce the metabolic costs, and mitigate the risk of injury. But there's a big challenge here. Just quickly, I put knee braces exoskeletal in Google. You see around 1 million results come out. So if you want to select a relevant assistive device, how can you do that? Do you want to select, even if 50, 60 that you have in mind, you want to take them in the lab or the field and then test them all? So you see that's a lot of challenges actually happens here. And here is another example that so many of them out there. So we really need to know what to do with basically selecting or optimally selecting assistive devices. So assistive devices is one thing, and knee injuries, as you all know, is a common injury or musculoskeletal injury in military and sporting activity. So we want to focus today on knee injury and assistive devices. And knee braces in particular are common in use. So what I'm going to talk today and the methodologies that we are developing can be used for a variety of exoskeletal systems, but for simplicity, we focus on knee braces. So these are the main questions that we have in order to assess assistive devices. How can we assess and select the right assistive device, and which biomechanical or design parameters are critical in this process? So let's please have this in mind as we go. As I just talked about this a little bit, and you notice in great discussions today, so we have experiments. So you actually can buy and do the experiments, biomechanical experiments in the lab or in the field, and get the ground reaction forces, the joint kinematics, joint kinetics, or you actually can put them all in a computer model, like a simulation musculoskeletal models or biomechanical models. So there are these two traditional methodologies that we have. So what we are going is basically kind of hybrid methodology. So how we can actually put these two together. Let's go one step back in terms of, so what I would like you to consider is we have a design process and we have a selection process. So sometimes they should go hand in hand, right? So you design something so that the person who is using end user can select it easier, right? But because of the variety of applications, sometimes it's not really easy to keep the end user in mind, right? So usually what happens in engineering design, you have something in mind, you have conceptual model, you say intention objective of the design, then you develop in a kind of CAD, sort of a computer aided design program. Then it's an iterative methodology. If you have a company, for instance, so you have a prototype of it, and then you try to basically use some sort of assessment technologies, and then you go back, improve your design, and go on until you get your final product. But what you can see here, you see that, as I said, the human in this loop may not be present all the time. When a company basically build it, so it doesn't consider every single person. So it's not subject to specificity as well as the human in the loop in this process. So if you look at, for instance, some of the parameters that affect your design or your selection, I just listed them here. For instance, if you have you add a simple brace to the system, to your knee. So the muscle EMGs or neural commands, or if you talk about gait, special temporal measures or muscle diet, everything would change, right? And you have other parameters from the exoskeletal system or a brace. its weight, its size, its mechanical stability. So you sort of need to consider all of them if you want to consider the interaction between the two. So again, going back to our objective, to investigate the role of assistive device here, a knee brace, we investigate the following: develop a hybrid methodology, assess an assistive device, and present a working model toward assessment of a knee brace. So speaking of knee brace, from a mechanical point of view, if you look at the simple knee brace, it's not that simple, but at least you can see how many parameters you have here if you want to design it or if you want to select it. There are stiffness, and at what angle, joint angle, that the stiffness starts triggering. You have upper and lower because at certain angle you don't want that to be triggered. At certain angle you want it to trigger, for instance, during gait, a damping or a transition, basically from which angle to the other angle, basically the stiffness starts triggering. So you see, even with simple brace, you have how many parameters to consider, right? What we are proposing is basically, you can see it here. We have human motion data. So imagine you collect data from the lab or from the field. So you have ground reaction force, kinematic, EMG data, for instance, and you collect, for instance, brace mechanical data. So you have the stiffness, damping of that particular brace. And then we put them together. So far, everything is experiments. And then we put them together in a musculoskeletal model. Now we actually can talk about the interaction. So what happens to the knee brace and what happens to the knee joint and overall the musculoskeletal system. And then we can actually predict, for instance, the knee joint, the joint kinematic, joint kinetic, muscle function, and so on. So if you look at the whole musculoskeletal system, it's basically neuromusculoskeletal system. So you have all these details, and if you add the assistive device, every single part can change, right? And then the movement, for instance, at the end would change. The brace itself, how does a brace affect? So if we simplify the effect of brace or exoskeletal to the knee joint or ankle joint, you can see just one gait cycle. And if this person has got a ankle brace, this person would feel the torque that comes from the knee brace, from the ankle brace to the joint. And in the meantime, the muscles also try to compensate, right? So there's a huge interaction in there. But in most of the studies that you basically see in the literature, they ignore this effect, how much is going because of the um, brace and how much actually the joint is working. Other people have focused on this problem from biomechanical point of view. They changed the stiffness of, for instance, the knee brace and then looked at the center of mass. And they see that if they increase the knee brace stiffness, center of mass also changes. So you see that even the pattern of movement changes this way. Or other people actually recently looked into one particular muscle here, soleus, at different stiffness condition of the ankle. Um, basically brace. So you can see that they start from 0, which is no brace, all the way to 30 Newton per millimeter. And you can see that at the end of the gait cycle, there is a big difference between the way that soleus basically works, or metabolic cost of soleus. So coming back to our methodology, I told you that we have human data and we have the exoskeletal and mechanical properties. Then the interaction, then we can actually talk a lot about kinematic, kinetic, muscle activity, and so on, because we have all these details in our biomechanical system or computational model. So what we did here was, you remember I talked about the different parameters of the knee brace. We just kept everything the same and just changed the upper stiffness. So you see on the first row, we changed the upper estimate from almost 0 all the way to 4 SI unit, and the rest is quite similar. It's basically similar. So you just wanted to study the effect of upper stiffness. So our results shows that this is a torque, or the torque because of the knee brace in one gait cycle, the x-axis gait cycle, one gait cycle. You see that when it is the knee stiffness is almost 0, so there is basically no torque applied from the brace to the knee joint. And as you increase the stiffness, you see a dramatic change in the the interaction between the knee brace as well as the knee joint. And when you look at the metabolic cost, so speaking of performance, for instance, so it's quite interesting. You see that from 1 newton meter per degree in terms of the stiffness, all the way to 4, up to 25% the metabolic cost changes or increases. So this is the beauty of this type of modeling that we are introducing. So you cannot easily do this in the field or in the lab, but you can actually collect the data and then bring them all together, and then you can manipulate and understand what is the optimal, for instance, the stiffness that this person's metabolic costs would be increased or decreased depending on all the parameters that you involve. So in order to address this question of why this is happening, basically, we look into the effect of the role of braces stiffness on metabolic costs, and trying to distinguish brace basically effect and knee extension effect. So the knee extension effect is the red one. You can see here, these are all moments around the knee joint with different stiffness. You can see here different stiffness and in one gait cycle. And you can see that basically when there is no brace, everything goes through the knee muscles, basically how they are producing the torques. But as you move and change the stiffness of the knee brace, everything changes. So this is something that we need to consider when you want to select it. So imagine you are given a knee brace or exoskeletal system, and you can actually measure its stiffness. Then you can actually put it into this type of modeling and understand how much the knee is working and how much the brace is working. Is it really what you're looking for or not? So the next or the future directions would be, I don't know how many of you have seen this system that we have. This is the only one in Australia. It's called Karen system. Um, what we would like to do is this Karen system. Let me just explain a little bit if I have time. Yes, I have a couple of minutes. So this is similar to what you see in the traditional motion capture system lab, for instance, like you have Wycon system. We have here, you have basically treadmills, but the whole platform you can see here can move in all degrees of freedom. Is a robotic system there, and we have a virtual environment, virtual reality environment. We can have different scenarios, and it's a multi-sensory. You can change the auditory, you can change the basically the mechanical environment as well as the visual, as I told you in terms of the visual virtual reality. The force place, you have two force place like any other motion lab, and they integrate it, as I told you, in the design process. Sometimes the human in the loop is not there, but in this kind of systems we can have human in the loop. So we can have, for instance, different types of braces and then check what happens to the overall performance or injury mitigations. Thank you very much.
Thank you, Hussein. Again, please post your questions if you do have any. So I had one question. You know, if we're talking about the optimal characteristics of a knee brace, and forgive me if I missed this, you know, presumably, you know, it will depend on the person who's wearing it. So did those models, you know, can you put in for the human factors? Can you put in the like individual you know, human factors, or is it kind of just a general human characteristics that go into that model? Because presumably, as I said, yeah, like wouldn't the optimal knee brace sort of depend on the individual wearing it?
It's actually a very good question. Yes, we actually develop subject a specific model. So when I showed you, we have model and we have basically the mechanical properties of the brace. Everything is subject specific. So we actually develop subject specific computational model for the person, human, and then the same thing for the brace, and then put them together.
Wow, wow, that's fascinating. Thank you. Another question coming through: how does your logic generalize from knee braces to other assistive devices, such as an unpowered exoskeleton, DSTG, or DSTG's OX, or compression garments?
So the idea, as I showed you here, the idea here is what we wanted to show is look, there is an interaction, and this interaction is important, and it would affect the knee joint and muscles and the joint basically, and the overall performance. So the thing is, what we have done here is a parametric study, we call it in engineering, which means that we can actually change this now to any kind of exoskeletal system that we know the parameters. So because at the end of the day, if you buy something, you should know to some extent some of the parameters. Or if even if you don't know, we have methodologies to get these characteristics. So basically, first we get that characteristics. It's like a human motion. So basically, we want to know how this person walks, or the gait parameters, spatiotemporal parameters. We put them in the lab and we collect data, right? The same thing is for, let's say, exoskeletal system. So we have some parameters from that, and then we can actually, the model is so generic, so we can actually put them together as basically the question, depending on that question, basically. So it's very general, yeah.
Thank you. Another question: does your model account for skill/neuromuscular adjustments?
This is a very good question. So let's put it this way: musculoskeletal models, or the models that we develop, is definitely subject to specific. But the point is, whatever we design or we develop has to be validated, and we have kind of validated with experiments, right? Some of them are still generic. Some of them comes from, let's say, cadaveric studies. Some of them, it's like muscle parameters type of things. But we can, if we can, for instance, get EMG type of, which are very subject to specific, and then put them into the model, then it would consider the neural part of it. Or when some people actually consider like the EEG type of things, like the brain activity. And there are the possibilities, but at this stage, the model that I'm showing you may not exactly consider all these details. Yeah.
I think that's all that's come through. So thank you, Hussein. And thank you all for attending this afternoon's session so far. We're going to have a short break now. We finished a little bit earlier than planned, so we've got about a half an hour break, and we'll come back at 4 p.m. And we'll continue the session then. Thank you, guys.